So welcome to this lecture on VHDL in the course Digital System Design with PLDs and FPGAs. Last class we have completed the delay modeling and we have started some examples so that we apply what we have learned, and we couldn't complete that part. So I am planning to complete it, not only designing something, but give a code and kind of work out what is the possible circuit which it implements, or given to a synthesis tool what it synthesize, so that you get experience back and forth, given a circuit how to code it for synthesis, or given a code how to kind of make out what is implemented. It is very useful when you really work in a design team. You may have to work with something which is designed earlier, and most of the time it is done like that. You are in a team, you join a team, there is something going on and you will be given some responsibility. Many a times you will end up with some Verilog or VHDL code, and you have to add to it, modify it, debug it, and rarely there will be enough documentation. So to know, looking at the code, what is the underlying hardware it represents is a very useful thing to do. That is what we are going to do today, in addition to even designing some circuit. So let us quickly run through what we have done last class, and so that we can continue kind of smoothly from there, and let us move on. So this is what we have seen, the kind of an example program to illustrate the various delay models. So we have created a signal A. It's a kind of empty entity because we just wanted to see the waveforms, and we are using, instead of port, we are using everything as signal. We form an signal A with some pulses, and that is what is shown here, and X is A after 5 nanoseconds. So it has a pulse width, minimum pulse width 5 nanosecond, propagation delay 5 nanosecond, and so you get a delayed version of this with all the pulses less than 5 removed. Next is reject 3 nanosecond inertial A after 5 nanosecond, wherein it is exactly same, but everything below 3 is kind of rejected. So you get this, and this is a transport delay with a 5 nanosecond delay. So you get Z as a delayed version of A. That is what is shown here. And we also have looked at how to write a VHDL code to not only to synthesize, but to verify some timing condition on its input. Okay, it's quite useful, because sometimes you may have to, like you have some timing violation happening in the simulation, and you suppose it is random and you want to catch it, and you can do like that, do this way, though the timing analysis will show up, but definitely this is another way. Static timing analysis can report the whole time violation, the slack and all that, but yet this is a practice and a useful thing we are doing. So our aim is to write a code which checks the setup and hold time violation of the D with respect to the clock. So basic idea is to keep track of the event, this particular positive edge of the clock, and any event on the D. The idea is that when there is a positive edge of the clock, subtract the last event on D, make sure that it is greater than setup time. Similarly, whenever D changes, subtract the last event on the clock, then make sure that it is greater than the whole. So we have the entity here, we define two constants, setup time and hold time, to be conveniently kept in one place so that you can modify it in one shot, and we have a process with both D and the clock in sensitivity list which is required because we have to catch the event on D, and this is the behavioral code, and this is the main code which checks for the hold time violation. If there is an event on D, make sure is asserting the true condition that the time of the event minus the clock event is greater than the hold time, and update that time. And if there is a positive clock edge, assert that the time between that time and the last event on D is greater than or equal to setup time, and update the clock time, and that's how it is done. And as I said, at the 0 nanosecond we don't want it to report an error, so we make sure that that is avoided by this statement. And we have seen the syntax of assert a true or expected condition, and then if it is violated report a message, and you can specify what should the tool do by this level. For note and warning, it is just printed on the console, and for error and failure it just terminates the simulation process. So that is the syntax of assert. And then we started with examples. We have seen a VHDL code for a demultiplexer. The most proper code is this: when you have S is a select line, Y is the input, A, B, C, D are the output. When it is 0 0, Y goes to A, rest all are 0, 0 1, Y goes to B, then so on, C, D. So we have, this is ideal kind of coding for the most proper coding for the demultiplexer, because there is no priority, and for all the select line values we are specifying the output, and all the outputs are function of the same S and Y. So it is nice to combine this way, but there are many other ways to do it, and we have seen you can write equation for A, B, C and D in terms of the input and the select line. So this is A0 is Y0 not of S1 and not of S0, and when it comes to D it will be D0 gets Y0 and S1 and S0, because it is 1 1, and since it is a 1 to 4 4-bit demultiplexer, you have to write the equation for all the 4 bits. And now looking at this equation, seeing this symmetry, you can make out that this can be easily put it in a generate loop with index going from 0 to 3 for this, and this is fixed anyway, similarly for this and so on. So we can combine everything into generate loop, like for I in 0 to 3 generate A of I is Y of I, and that means you just take the first statement, put I here, similarly take this I here and so on, then you get this. And please remember that this is not a loop in a conventional sense, that like in a sequential language you go kind of execute one and execute the other. It's just a concise way of writing this like this, this is literally replicated 4 times and you get all the big equations. So it's a shorthand. You have to write with select for each output A, B, C and D. This is quite right, because no problem, because even in the hardware A output can be separated from the circuit for the A, can be separated from the B, absolutely no issue. If you write like that you get the circuit you want, but the synthesis tool has to infer now. They saying that ABCD is part of a single high level block called demultiplexer. I mean that's only trouble with this code. For these simple things the tools will do, but you have to be careful. Similarly you have the when else, you have 4 of them. A gets Y when I say 0 0, L 0 0, because we only talk about A output. Similarly B, C and D. Another version of the case, we don't say 0 0 everywhere, we make it at the beginning, then only change is indicated here. Then instead of case you can use if. There is like that if has a priority, definitely as it is written you say S is 0 0 then S is 0 1, that means not of 0 0, but since we are enumerating all possible values of S and when you say and S is not of 0 and 0 1, then everything reduces to same as case. So it's not a problem, this syntax doesn't give a problem, but still the most elegant code will be to use the case, and as in case you can initialize all the values at the beginning and represent only the change here. You could use another way is using an if for each of the outputs separate, like you say if S is 0 0 then A gets Y else A gets 0 0 end if. It is exactly like writing the with select or when else. Once again it is technically correct, but the ideal code would be to combine everything, all the outputs together as a function of A and Y. Another version is everything is initialized at the beginning and only the change is indicated here, and this is what we have maybe stopped at the last lecture. We are writing an 8-bit ripple adder. Okay, for the figure only shows a 4-bit ripple adder to save space, but the idea is same. You have the cascaded full adders. Full adders take A, B inputs, a carry input, and it produces a sum and a carry out, and the carry out goes to the next carry in of the next full adder and so on. Okay, and the issue with this ripple adder is that if you take the C4 or sum 3, it uses C3, and when you say you take the case of sum 3, in the worst case it propagates from C0 to C1, C1 to C2, C2 to C3 and C3 to S3. So there are, if you assume 2 levels of circuit in each of AND OR, then you have 8 gate delays by the time you come here, and you can imagine if you go to the S7 you will have the 16 gate delay, and that adds a lot of delay. Okay, so there are circuits ripple adders the adders which gives less delay, and so this is simple. You have the sum equation, sum of I is AI XOR BI XOR carry I plus 1 is AI at BI or AI or BI and carry I, which when you expand you get AB, AC and BC, C being the carry. And to make the code neat we have a C in which is C0 and C out which is say in our case C8. So to make the code clean, not to write everything in a single loop and not to write anything outside, we have defined a carry which is 9-bit, and we assign the carry 0 as C in and the carry out as C out as carry 8. Otherwise we will end up writing one assignment, one repetition for with C in for the kind of sum 0 and the carry 1, then the last one with the carry C out and all that. That is avoided by this game. Now also I mentioned is very unusual, like all the combination. Many times when you read the textbook you will design lot of combination circuit which is all designed with a truth table. When it comes to the adder, somehow surprisingly you kind of quickly make a full adder then cascade it, but that is, I mean, if you go by the principles of what you have learned, if you want an 8-bit adder, then you make a truth table for A and B which are 8-bit, so it will be 16-bit 64K truth table. Yeah, one definitely we cannot work it on the paper. Then you implement a circuit which essentially should give you an AND OR circuit which is 2 level or 4 level or whatever depending on all the complexity. So actually if you do that, what you get is a carry lookup adder, and since that is complex, one should go for a modular approach. At least in the case of the adders it is possible, because of this structure you add something, then you have a carry which is going to the next level, and the next level you do the same thing. So because of the modularity, because of the symmetry, it is possible to design a kind of modular ripple adder, modular adder. It may not be possible in every case, things can be not very symmetric or regular. So many times it is not amenable to such scheme, but this at least is amenable to that, so we do this, okay. So that's a basic game. Now so as I said, now as you are taught, the kind of carry look ahead adder is derived from here, not an issue, but the basic game is that in a carry look ahead adder is that when it comes to this stage, instead of using something already defined, this stage will work with B1 A1 B0 A0 Z0 to generate both S1 and C2, that is a basic game, okay. Or when you come to the stage third stage, instead of just using B2 A2 S2 and already formed C2, we will use B1 A1 B0 A0 Z0 C1 everything, I mean to generate, so that in one shot it is generated, not rippling through the stages, that is a game. So let us quickly, maybe that gives a kind of revision and some practice in coding, that is what shown here. So this is the adder equation, S of I is A of I XOR B of I XOR C of I, no confusion whether be it ripple adder or carry look ahead adder, the thing is changed, the game is not, there is nothing complicated with that. The problem is here, so we attack that. So C of I plus 1 is AI BI or AI or BI and CI, and this is now for clarity, this is called generate G AI BI, because if both are 1 1, you know that the sum is 0 and there is a carry out, definitely there is a carry out, okay. Irrespective of the carry input to that stage is 0 or 1, if both are 1 1, the sum is 0, carry out is 1. If the carry input is 0, no change, if the carry input is 1, sum will become 1, the carry out is 1, so absolutely no change. So that is called generate, the carry is generated at this stage. But if any one of them is 1, AI or BI is 1, then the carry is generated if input carry is 1, okay. So C1 is 1 if A0 or B0 either of them are 1 and C0 is 1, that is a game. So we call that is propagate, that means if AI or BI, the carry before the carry input is propagated to the carry output. So we define two things, GI which is AI BI, AI or BI. Now the game is very simple, like you say you take this C2 is nothing but A1 B1 or A1 or B1 and C1. Now usually the C1 comes from the previous stage, okay. So what is done is that you substitute the equation for C1 here and expand it and you get a 2 level AND OR, okay. That's only the game, that is what is the carry look ahead adder. So the problem is that as you go the higher indexes, because it is expanding, more and more product terms will come in the implementation, that is what is shown here. You can work it out, I think maybe you have studied. So it is very simple, C1 is nothing but G0 which is A0 B0 or kind of A0 or B0 and C0, so that is P0, okay. Similarly when you come to the next stage, C2 is A1 B1, that is G1, okay, or A1 or B1 and G0, G0 is nothing but what is generated in the previous, which is the carry input to this stage, so which is nothing but A0 B0, okay, or A1 or B1 and A0 or B0 and C0, and that is how the propagated from the beginning, okay. So when it comes to the third stage, you have kind of 3 AND gates and 1 G2, which is nothing but the kind of A3 sorry A2 B2 and so on. So it goes like that. So even if you put say G0 is nothing but an AND gate here, P0 is an OR gate here, so you get a 3 stages of delay for any of the stages. There is rippling is avoided, but it's a very complex circuit, and now at least at a simplistic level we will not be able to write a loop, because the sum is no issue, sum is simple, but the carry is something which go on expands. So with a signal, as we have learned now, it is very difficult to write a carry lookup adder. You can write with variables. Since we have not looked at it, we will delay that kind of coding for a moment. So we will just look at this code, the equivalent code in VHDL, that is what we are going to do. So I am not showing the entity is same. You have like in the previous, AB is 8 bit, sum is 8 bit, there is a C in and C out, there is a signal which is internal signal which is kind of 9 bit. So that all holds good here, but in addition we need now G and P, generate and propagate, which is for each stage. So we have an 8 bit vector. As early in the earlier case we have the carry 0 which is C in, carry out C out which is carry 8. Now we write a loop not only for the sum but also for GI and PI, because that is regular, every stage need that. Only thing is that maybe the second stage use the not only G1, the G0 also it is using, but does not matter, we can generate it parallelly in a loop. So this is the loop index, loop label. For I in 0 to 7 generate, G of I is AI and BI, P of I is AI or BI, and sum of I is AI XOR BI XOR carry I. Now we are forced to write it each carry equation separately. The carry 1 is G0 or P0 and carry 0. That is shown here, G0 or P0 and carry 0. Similarly carry 2 is G1 or P1 and G0 or P1 and P0 and carry 0. G1 or P1 and G0, P1 and P0 or C0. Similarly it goes, and you have to write up to carry 7. Doesn't actually matter, because many a times you write an 8 bit or 16 bit or 32 bit, maybe even 64 bit. Luckily we are not yet in 128 bit, we are the number representation as on now like double precision, it can be 64 bit. So it is not a big deal, even if you do not write a loop you can still implement that, and just because the code is longer you will not end up with any bigger circuit. Luckily this is hardware, not a C code, but definitely if you write this scheme in a C, it might kind of similar style. In C you might get a very you might take a longer time to kind of execute such a code, not a problem in hardware, though we will definitely see how to write that in a loop. So but after all this is for a practice, we have looked at the ripple adder code, we have looked at the ripple adder, carry lookup adder, but when it comes to the VHDL, normally you want an adder, you just write it's an 8 bit adder, then AB is 8 bit vector, sum is 8 bit vector, just say sum gets A plus B. If you want to carry out, we have discussed in the arithmetic section how to write that, we have seen that. You can adopt that scheme, but now when you write such a scheme, it depends in the library code of the tool how this plus is written. Okay, it will mostly will end up with a ripple adder. When it comes to FPGAs or PLDs, at least in FPGA there are kind of dedicated adder resource, we will see that they will use that built in resource to implement the ripple adder, which will be much faster than implementing any other adder, be it a carry lookup or carry select or carry skip or whatever you say. A symbol plus in the case of FPGAs will be much faster because it is in silicon, built into the silicon, but if you do anything else it will use the programmable wires, which is going to add delays, and it is going to occupy a lot of logic resources which need to be interconnected, and it is going to be delayed. So ultimately when it comes, though we have done some practice with the adder, when it comes to an adder really we are going to use most of the time the plus operator within that. So let us take an example of a shift register. Those who have done an undergraduate program, sometime it is a little bit you are confused about the shift register, because somehow this shift is kind of coupled register. You have learned a block called shift register in a very particular, very restricted fashion, and it very simple thing is made very complicated. Okay, so when you say shift, okay, suppose you have a register, 8-bit register, D7, D6 up to D0. Okay, this is a MSB, this is a LSB. Suppose you want a left shift by 1. Okay, you like this is stored in a register, you want to output say suppose this is kind of saved for it is there, it is not changing, and you want a shifted version of this left shift by 1. Okay, it is very simple. You take the D6 as the shifted version of for the 7, D5 is used as D6 or D-6, D0 is used as, sorry this is this is D-1, I will change that. So this is D-1 and you append as 0. So basically when you say shift alone, it is just a wiring. When you say a fixed shift, okay, when you say shift left by 1 or shift right by 2, it is always a wiring, there is no hardware is required. Okay, absolutely, you take this 6 as 7 here, 5 as 6 and 0 as 1. Okay, shift left and you append as 0. So it is just a wiring, but now you want to store, and suppose this is changing and this is changing continuously, streaming as in a pipeline, then you need to store this somewhere, and that can be stored in a separate register. Mostly it is done like that, very rarely that it is pushed back to the same register. In a serial circuit you will be any computation that will be stored in a separate register, but it can be pushed back to the same register, and that is what you have studied in undergraduate. So anytime you say shift, this particular picture comes to your mind, and sometime it can create little kind of confusion. So that is what I have shown here. You have a source register, some kind of wiring for a fixed shift, and destination register, and wiring could be whichever way you want. Maybe it's everything is shifted by 4, that can be kind of all the LSB least significant go to MSB. When it comes here, maybe this part can come down here depending on the requirement. Okay, so there are it depends on the application, the computation, but this is what you have learned, where the source and the destination register is same. That means you take the queues, you have a register which is kind of, okay, this maybe can be called Q also being the output, but I hope the concept is clear. Then here you take the Q, shift it and put it to the D of the same register. Okay, that is a shift register. Now suppose what happens if it is the shift is variable. That means when some control signal is active, then you say let us call one control signal called left or right. If the left or right is 1, then do a shift left by 1. If it is if it is 0, then shift right by 1. So the shift is variable now, either shift this way or shift that way. That definitely you cannot wire it, because now depending on the control signal you have to get this or that, and that shows a mux. Okay, you have to have a mux. So when you have a variable shift, then you need to use a multiplexer. So I am showing a scheme wherein either say you take the Q6, the D6 part, I am showing just one, then if it is a shift left, then the Q5 is pushed here. If it is shift right, the Q7 is pushed. If not, if either of that is not true, then maybe the same thing can be pushed. Okay. Now it depends on the select line. If select line is only 1 bit, then you can choose between those two. If it is 2 bit, then if it is for 0 0, you retain the same, you pass the same. If it is 0 1, do the shift left. So 1 0, you do the shift right. 1 1, again maybe the pass the same or whatever. Okay. So when you have a variable shift, you use multiplexer. In this case it is an 8 bit register, so you can use 8 multiplexers, which is all 3 to 1. Okay. But it is possible to view instead of 8 kind of single bit multiplexer, maybe you can view it as a kind of huge 8 to 1 8 bit multiplexer. That means that you assume a huge 8 bit multiplexer here, the output is going to all the 8 registers, and there is connection here to all the inputs and so on. Okay, can view it that way also, there does not matter, and you can have the coding also written that way, whichever way is convenient. So let us look at a universal shift register which allows you to do the shift left, shift right, and you can hold the value the same, or you can parallelly input some value. Okay, like you can load it parallelly, you can shift left, you can shift right. So we have a register which goes from D7 to D0. When you are shifting left, there is an input called Ln which goes to Q0, Q0 go to Q1 and so on. Okay, and similarly when you are right shifting, the Rin goes to the Q7 and Q7 go to Q6 and so on. And okay, I have not shown the clock, but the clock is there, reset is there. So the select line, now so we have for take the case of a 6th or the 7th stage Q6, then the D6 you have a mux here which is 4 to 1 mux. So we have 2 select line, when it is say some value Q5 for shift left comes, when you want a right shift the Q7 is put in, and if you want parallelly load something, then this input which is coming from the outside PI6 is loaded, the 6 bit, and if it is not, you retain the value, you recirculate the value. Okay, and this mux is repeated kind of 8 times. So that is what the real the hardware is, and now we write the code, and when we write the code you could write it as one kind of 4 to 1 mux single bit repeated 8 times, or as I said you can have you can think of a huge mux where the 8 bit output is there, and input is also 8 bit, because after all we are connecting all the inputs down here. So but it is you can expand it to bring clarity to it. So whichever way you view it, but that is hardware. So this is the library close for it, and this is the entity where clock and reset are the input, left in right in is a input all single bit. Select line is because the 4 to 1 multiplexer you have 2 bit, parallel in is 8 bit because this is an 8 bit register, and the Q is also 8 bit. Okay, now you can sense already that Okay, now I am showing there could be a little yes, okay. So we have to maybe kind of assign a signal, and we have to declare a signal called Q here, which I have not done, but we can do that. Instead of a port here we will declare a signal. You imagine that this has some other name and we have a signal Q here, because we are somewhere we are going to say the Q is going on the right hand side, not the right thing to do. So we have to declare this a signal. Sorry for the minor error, but assume that the Q is signal here. So now we say process reset clock begin. If reset is 1 then Q is other 0. We are resetting all the register contents. Else if clock tick even, clock is equal to 1, then case select is parallel load. When 0 0 we are parallelly loading, Q gets P in, that means Q 7 down to 0 get Pi P in 7 down to 0, that is the meaning here. Then that is a parallel load. Shift left when 0 1 Q0 get L in, so that is the Q0 is getting the L in, and then we can write a loop where for I in 0 to 6 loop Qi plus 1 get Qi. For the shift right Q7 get the write in, you can say write in, and Q6 get the Q7, that means Qi gets Qi plus 1. It's opposite to that end loop. And if others in other case, that means when 1 1 is there or all other cases Q gets Q. Okay, since we are saying Q is coming at the right hand side, this has to be a signal, it cannot be an output. So for simple cases you don't verify, so that is why it happens, you just write the code. Now you can also write, that is code, and this is how you should design, simple thing, but when you start you draw the block diagram and you write the code, and after a while this will be in your mind for simple things at least. So you can still code it with this in keeping this detail in the mind, but the complex thing at least all the blocks should be shown so that everything is clear. So let us write this instead of the loop as a single mux, that is what we are going to write. That is how the code is here. If reset is 1 then Q gets other 0, else if clock tick even, clock is equal to 1, case select is when 0 0 Q get P in, but when 0 1 we are going to see it as a single mux now. Q7 down to 0 get Q6 down to 0 and L in, okay, that is what is shown here. Q7 down to 0 gets Q6 down to Q0 and L in. Now this part get this part, that is what is shown here. And for the right shift it is opposite, Q7 down to 0 get Rn which comes at MSB and Q7 down to 1, okay. So Rn go to Q7, Q7 go to Q6 and so on, and when others Q gets Q, okay, that is a code, and this is the most elegant code as far as the universal shift register is concerned. So let us take another example, okay, which is little bit kind of arbitrary. So please have a look at the circuit. Okay, now this shows first of all an 8-bit register, because you know that this output is said 7 down to 0. So this definitely are 8 flip flops, 8 D flip flops, the clocks are connected together, reset is connected together, 8-bit register. The output is combined added with an A 7 down to 0, that goes here to a 2 to 1 mux, and when a signal called LOC is there, then when LOC is 0 the B gets loaded, LOC is 1 this sum get loaded, okay. Now we have seen that a set of registers with a preceding combination circuit can be coded in a single process. So we are going to write a single process for this, but the question is what about this, okay. Now this looks like, at least in the picture it looks like it comes afterwards, but then you know that this is a kind of circle and this is also behind, though it uses an input called Q, this plus, this adder comes here, you know. So you can transform this block schematic like this, you know, it is same. We have, you know, the plus is put here and Z is taken here, you know, it's exactly same. Now we can look how to code it, you know. So we know that how to code a flip flop. You write a process with clock and reset. If reset is 1 then this Z will be other 0, or the appropriate, you know, we might use a signal because this is used internally. So we can define some output, assign that and all that. Then everything is synchronous, it is upon the clock. So we say in the clock event clock is equal to 1. If LOC is 1, LOC is 1, then we say this output gets A plus Z, okay, else it gets B, that's all, okay. So I suppose you get the picture. So we say that if LOC is 1, the output is upon the clock, it is under the clock, A plus Z, else it is B. So it is very simple code. So we have the library declaration, the package 1164 and unsigned, mainly because we are going to use this plus, and plus is overloaded for standard logic in this particular library, and this is a entity, okay. Now mind you, I have put some kind of arbitrary name for it, but because when you kind of give a example like that, you should not write some obvious name so that the students can detect it. So this is how I write the kind of questions. Whenever I give a question, I don't write a counter or some legible name, or even, you know, even these names sometime I change so that is not easily obvious, like when you go back from a VHDL code to the block diagram. So here the ports are clock and reset and LOC are single bit input, AB which is 8 bit input, Z is an 8 bit output. As I said, since we are going to use Z as an input, we are going to define a signal called Q, which is also 8 bit, and we assign Z, the Q to Z, so that we can use Q being a signal internally. So this is the main the code, a single process for this. So if clock event process reset clock begin, if reset is 1 then Q is other 0, else if clock event clock is equal to 1, then we say if lock is 1 Q gets A plus Z, else B. So that is it. If lock is 1 then Q gets Q plus A. Yes, this is instead of Z we are saying Q plus A, because Q is the signal, Q plus A, else Q gets B and if. So this is the one which is representing the 2 to 1 marks, and this plus represent the adder which comes before the 2 to 1 marks, and everything being in the clock event clock is equal to 1, it goes to a register, or you get it goes to the D of the registers, all the bits, you know, the Q7 goes to the D7 and so on, okay. And say end if for this one, this is the end if for this, end process for this, and the architecture, okay. As I said, you intend it properly so that people can make out. After an experience, you know, you look at the code, you know, you can draw the block diagram. So that is how this particular block diagram is easily, very easily. So just you have the picture here, you can write the code, or you can even tell your team members to write the code. Suppose many times you are designing, you don't have to write the code, you know, you come to a block level RTL diagram and give it to somebody who can code it, and the coding is not a big deal, designing is a big deal. Once you get to know, come to this level, then the coding is one to one. Just look at the picture and you write few lines of code, it doesn't matter. You see this much, you have a register 2 to 1 mux and plus, and it does something that is all coded in a very few lines, 1 2 3, maybe when I say line 3 4 5 lines it can be coded, because there is very few lines are required to bring the hardware to code the hardware. Okay, now let us do the opposite. Okay, here what we have done is that we have given the circuit or known the circuit, we have go ahead written the VHDL code, and we have done that for a very simple known circuit like the ripple adder, the carry lookup adder, the shift register, and now we have given some kind of random circuit without worrying its functionality, and we have coded it. It's simple. As soon as you put this kind of the block diagram, then you can code it. Now we do the opposite. Somebody has given you a circuit, okay, sorry, a VHDL code. You have to kind of make out what the circuit or the block diagram or the RTL, whatever you call, is. Okay, that's a basic game here. So let us see, and as I said, I have made the entity something, input something, some kind of random names. I have not given any kind of sensible name to it. I have not shown something is input, something is reset, nothing, it is just ABCD. So let us see whether we can make out what is the kind of circuit. So we have the library close package 1164 for standard logic, package unsigned, maybe for the I don't know for what, maybe the just the plus, if there is plus, and standard logic arith maybe for this kind of relational operator, maybe I have to check, you can check that. And this is the entity, and in that we have 3 single bit A, B, D single bit input, 1 input which is C which is 8 bit, 1 output which is Z which is also 8 bit. Okay. Now in the architecture we have given some name arc underscore this name of this is the name, and we declare a signal Y which is also 8 bit. So naturally one can assume it is something related to Z, and the begin Z gets Y. So we Y is nothing but Z. We are kind of circumventing the trouble with output signal that cannot come on the right hand side. So the moment the Y comes, it is nothing but Z. Now we have a process as the main code which has A and B in the sensitivity list. So we are sure that A and B are inputs, okay, and you say begin, and you say if A is 1 then Y is other 0, else if B tick even and B is equal to 1 then, and that is end if here. Okay. So we are very clear looking at this code that this is nothing but a register, and Y being in the assignment, it is an 8 bit register where A is the reset, asynchronous reset, and B is the clock. So we can already draw a 8 registers with A connected to asynchronous reset, B connected to the clock. Okay. Now whatever is written here comes to the D because that is synchronous, that is written within it, and you see that it say that Y which is the output itself equal to C which is input. That means whatever was the register output is taken is compared with C. If it is 1, okay, if that is 1, then you see Yi plus 1 is Yi and Y0 is D. So it's a kind of shift or a mux which is doing the shifting. It's a single bit shift which is a left shift, the least significant bit gets D. So that's all. So it's a register where A is a reset, B is a clock, the input is a shift register. The shift register work if Y equal to C, that means otherwise it remembers its own value. We do not say else, so it remembers its own value. So that means Y is equal to C, go to a 2 to 1 mux, which is the Y equal to C output is the select line of that mux. At the input of the select line is a shift, or the same value goes to the input. That is it. So that is what is shown here. We have an 8-bit register, so these are thick lines, 8-bit. The output is Y, which is same as Z, and the clock is B, reset is A, and the Y goes to compare with C, and the output of it's a select line which select a mux. When it is 1, then the shifted version of the Y along with the D, Y6 down to 0 and D goes to the Y, otherwise it retains itself, it recirculates itself. That is what is the code shown here. So maybe you have one more nested if, then if there is another if inside that comes before, okay. You know that this is the highest priority. If you write one more if, that comes before that, that is simple like that, it goes like that. You start with here the first if, the second if, third if, and so on, okay. So that is how the block diagram is drawn, very simple. If you nothing to worry, like if somebody dumps a huge code to you and you don't know what to do, then you sit quiet, go from top to bottom. At the beginning you will be thoroughly confused, you will curse your boss, and don't worry, sit with the code, look at it again, start to write, look at the signal, start writing what are the signal, what are the sub blocks, maybe the process, maybe procedures. You start making a simple note of each block, what could be that, and start drawing pictures. Gradually things will emerge, the clarity will bring, it will come up, and you will be able to decode all the circuit. Maybe after drawing the circuit you will even find that it could have been coded much better way, in a very simple way, elegant way, concise way, and which is documentation wise better, and so on. So that is how I have illustrated this. And okay, let us take maybe another example. I don't know whether I will be able to complete this, but let us look at it, at least let us start with it. So here it is a little more complex, okay. I have cooked up something so that to little bit confuse you, but to kind of to make some sense out of it, okay. So we have library 1164 package, unsigned package, because somewhere we are going to use plus or something like that. Some entity, UV are the input, which is 4-bit, W is output, which is 8-bit, okay. Now I tell you, if you get this in a test paper or an exam, you should apply, you should apply your mind. There is one thing in real life where you have to get to the answer quickly, though I am not kind of convinced that the testing somebody's competence is by doing things fast. Doing things fast represents some experience, may not be the intelligence or capability, but an experienced guy can do things faster, which is many times you don't have to design so fast as a sprint or something like that, but it looks the present situation looks like that. Everybody is kind of working hard to keep the Moore's law true, or every 2 months you have to have a new cell phone, which is not really required, frankly, in my opinion. But when you have such a problem, you should, my advice is that you should guess probably what is this kind of circuit which takes 2 4-bit value and 1 8-bit value. Sometime looking that will bring some clarity. You have to do some kind of investigation, somebody called detective work or research, somebody called whatever. You should be able to give a guess. So let us come to architecture declaration region. Now there is something funny happens here. There is a type D type 1 is array 3 down to 0 of standard logic vector 3 down to 0, okay. Now we are declaring a D type 1 as something which is a 4 values each of which is 4 bit. Okay. Now and we have declared a signal called y which is same as this. That means it essentially means y3 is a 4 bit vector, y2 is a 4 bit vector, y1 is a 4 bit vector, y0 is a 4 bit vector. Okay. So for whatever reason it is defined like that, that is how it is defined. You have 4 values each of which is 4 bit, and we have declared y. So you have y3, y2, y1, y0, or other way y0, y1, y2, y3, each of which is 4 bit. And when it comes to the this one, another data type which is type D type 2 is something similar, is array 3 down to 0. So it is a 4 values or 4 locations of 7 bit. So this is 4 locations of 4 bit, this is 4 locations of 8 bit, 7 down to 0, 8 bit. And we have declared a signal x which is of this type D type 2. That means you have x3, x2, x1, x0, each of which is kind of 8 bit. Okay. So we have declared 2 signals y which is y3, y2, y1, y0 4 bit, each of which is 4 bit, and x3, x2, x1, x0 each of which is 8 bit, and we are declaring a constant called temp which is a 4 bit vector which is initialized to 0. That means this is nothing but like 4 bit 0, 4 zeros. Okay. That is what is declared here. Maybe now we are coming to the end of the lecture, so we will see what is the code here, and we will kind of look at it, how to decode what is written in the code, come out with the proper circuit for it. That is what we are going to do. So that gives a good practice, that is my idea, going from the circuit to the code to circuit and so on. So in this today's lecture we have seen basically the carry look ahead adder, a symbol adder with a plus operator. Then we have looked at the shift register which is fixed shifting, which is nothing but wiring with registers, then the variable shift with multiplexers, and then we have seen a universal shift register. We have put some arbitrary block diagram and we have written the code, and now we are again back to some code to work out the block diagram. So I suggest now look at these examples and work out your own example and practice it. Okay. So I wish you all the best and thank you.